In the last video, we developed an anomaly detection algorithm. In this video, I'd like to talk about the process of how to go about developing a specific application of anomaly detection to a problem. And in particular, this will focus on the problem of how to evaluate an anomaly detection algorithm. In previous videos, we'd already talked about the importance of row number evaluation, and this captures the idea that when you're trying to develop a learning algorithm for a specific application, you need to often make a lot of choices, like choosing what features to use and so on. And making decisions about all of these choices is often much easier if you have a way to evaluate your learning algorithm that just gives you back a number. So if you're trying to decide, I have an idea for one extra feature, do I include this feature or not? If you can run the algorithm with the feature and run the algorithm without the feature and just get back a number that tells you, did it improve or worsen performance to add this feature, then it gives you a much better way, a much simpler way with which to decide whether or not to include that feature. So in order to be able to develop an anomaly detection system quickly, it's really helpful to have a way of evaluating an anomaly detection system. In order to do this, in order to evaluate an anomaly detection system, we're actually going to assume that we have some labeled data. So far we'll be treating anomaly detection as an unsupervised learning problem using unlabeled data. But if you have some labeled data that specifies what are some anomalous examples and what are some non-anomalous examples, then this is how we actually think of as the standard way of evaluating an anomaly detection algorithm. So taking the aircraft engine example again, let's say that you have some labeled data of a lot of just a few anomalous examples of some aircraft engines that were manufactured in the past that turned out to be anomalous, it turned out to be flawed or strange in some way. And let's say we also have some non-anomalous examples of some perfectly okay examples. So I'm going to use y equals 0 to denote the normal or the non-anomalous examples, and y equals 1 to denote the anomalous examples. The process of developing and evaluating an anomaly detection algorithm is then as follows. We're going to think of as the training set. We'll talk about the cross-validation and test sets later, but the training set, we usually think of this as still the unlabeled training set. And so this is our large collection of normal, non-anomalous or not anomalous examples. And usually we think of this as being non-anomalous, but it's actually okay even if a few anomalies slip into your unlabeled training set. And next we're going to define a cross-validation set and a test set with which to evaluate a particular anomaly detection algorithm. So specifically for both the cross-validation and test sets, we're going to assume that we can include a few examples in the cross-validation set and the test set that contain examples that are known to be anomalous. So the test set, say, we'll have a few examples with y equals 1 that correspond to anomalous aircraft engines. So here's a specific example. Let's say that altogether, this is the data that we have. We have manufactured 10,000 examples of engines that, as far as we know, were perfectly normal, perfectly good aircraft engines. And again, it turns out to be okay, even if a few flawed engines slips into this set of 10,000 is actually okay, but we kind of assume that the vast majority of these 10,000 examples are good or normal, non-anomalous engines. And let's say that historically in however long we've been running our manufacturing plant, let's say that we end up getting 20 flawed or 20 anomalous engines as well. And for a pretty typical application of anomaly detection, the number of known anomalous examples, that is with y equals 1, we may have anywhere from 20 to 50 would be a pretty typical range of examples, number of examples that we have with y equals 1. And usually we'll have a much larger number of good examples. So given this data set, a fairly typical way to split it into the training set, cross-validation set, and test set would be as follows. Let's take our 10,000 good aircraft engines and put 6,000 of that into the unlabeled training set. So I'm calling this an unlabeled training set, but all of these examples are really ones that correspond to y equals 0 as far as we know. And so we would use this to fit P of x, right? So we would use these 6,000 engines to fit P of x, which was that P of x1 parameterized by mu1 sigma squared 1 up to p of xn parameterized by mu n sigma squared n. And so it would be these 6,000 examples that we would use to estimate the parameters mu1 sigma squared 1 up to mu n sigma squared n. So that's our training set of all good, or the vast majority of good examples. Next, we would take our good aircraft engines and put some number of them in the cross-validation set, put some number of them in the test set. So that's 6,000 plus 2,000 plus 2,000. That's how we split up our 10,000 good aircraft engines. And then we also have 20 flawed aircraft engines, and we'll take that and maybe split it up, put 10 of them in the cross-validation set and put 10 of them in the test set. And in the next slide, we'll talk about how to actually use this to evaluate the anomaly detection algorithm. So what I've just described here is probably the recommended or pretty good way of splitting the labeled and unlabeled example, the good and the flawed aircraft engines, where we use like a 60-20% split for the good engines, and we take the flawed engines and we put them just in the cross-validation set and just in the test set. And we'll see in the next slide why that's the case. Just as an aside, if you look at how people apply anomaly detection algorithms, sometimes you see other people split the data differently as well. So another alternative, this is really not a recommended alternative, but some people will take of your 10,000 good engines, maybe put 6,000 of them in the training set, and then put the same 4,000 in the cross-validation set in the test set. And so, we like to think of the cross-validation set and the test set as being completely different data sets than each other. But in anomaly detection, for sometimes you see people sort of use the same set of good engines in the cross-validation set and the test sets, and sometimes you see people use exactly the same sets of anomalous engines in the cross-validation set and the test set. And so all of these are considered less good practices and definitely less recommended. Certainly, right, using the same data in the cross-validation set and the test set, that's sort of not considered good machine learning practice. But sometimes you see people do this too. So given the training, cross-validation, and test sets, here's how you evaluate, or here's how you develop and evaluate an algorithm. First, we take the training set and we fit the model P of x, so we fit all those Gaussians to my m unlabeled examples of aircraft engines, and then these are, I'm calling them unlabeled examples, but these are really examples that we're assuming are good or the normal aircraft engines. Then imagine that your anomaly detection algorithm is actually making predictions. So on the cross-validation of the test set, given a, say, test example x, think of the algorithm as predicting that y is equal to 1, if p of x is less than epsilon, it's predicting 0 if p of x is greater than or equal to epsilon. So it's trying to predict, given x, it's trying to predict what is the label. Is it y equals 1 corresponding to an anomaly, or is it y equals 0 corresponding to a normal example? So given the training, cross-validation, and test sets, how do you develop an algorithm, and more specifically, how do you evaluate an anomaly detection algorithm? Well, to do so, the first step is to take the unlabeled training set and to fit the model P of x to the training data. So you take this, I'm calling it unlabeled training set, but really these are examples that we're assuming the vast majority of which are normal aircraft engines, not anomalies, and we're going to fit the model P of x. We're going to fit all those parameters for all the Gaussians on this data. Next, on the cross-validation of the test set, we're going to think of the anomaly detection algorithm as trying to predict the value of y. So in each of my, say, test examples, we have these xi tests, yi tests, where y is going to be equal to 1 or 0, depending on whether this was an anomalous example. So given input x in my test set, my anomaly detection algorithm, think of that as predicting that y is 1, if p of x is less than epsilon, so predicting that is an anomaly and the probability is very low. And we think of the algorithm as predicting that y is equal to 0 if p of x is greater than or equal to epsilon, so predicting that it's a normal example if the p of x is reasonably large. And so we can now think of the anomaly detection algorithm as making predictions for what are the values of these y labels in the test sets or in the cross-validation set. And this puts us somewhat more similar to the supervised learning setting, right, where we have like a label test set and our algorithm is making predictions on these labels, and so we can evaluate it by seeing how often it gets these labels right. Of course, these labels will be very skewed because y equals 0, that is normal examples, will usually be much more common than y equals 1, than anomalous examples. But this is much closer to the sorts of evaluation metrics we can use in supervised learning. So what's a good evaluation metric to use? Well, because the data, because the data is very skewed, because y equals 0 is much more common, classification accuracy would not be a good evaluation metric. So we talked about this in the earlier video. If you have a very skewed data set, then predicting y equals 0 all the time will have very high classification accuracy. Instead, we should use evaluation metrics like computing the fraction of true positives, false negatives, true negatives, compute things like that, or compute the precision and recall of this algorithm, and, or do things like compute the F1 score, right, which is a single row number way of summarizing the precision and the recall numbers. And so these would be ways to evaluate an anomaly detection algorithm on your cross-validation set or on your test set. Finally, earlier in the anomaly detection algorithm, we also had this parameter epsilon, right? So epsilon was this threshold that we would use to decide when to flag something as an anomaly. And so if you have a cross-validation set, one way to choose this parameter epsilon would be to try many different values of epsilon, and then pick the value of epsilon that, let's say, maximizes F1 score, or that otherwise does well on your cross-validation set. And more generally, the way to use the training, testing, and cross-validation sets is that when we're trying to make decisions like what features to include, or trying to tune the parameter epsilon, we would then continually evaluate the algorithm on the cross-validation set. So we make all those decisions like what features to use, how to set epsilon, use that, evaluate the algorithm on the cross-validation set, and then when we've picked a set of features, when we've found the value of epsilon that we're happy with, we can then take the final model and evaluate it, do the final evaluation of the algorithm on the test set. So in this video, we talked about the process of how to evaluate an anomaly detection algorithm. And again, being able to evaluate an algorithm with a single row number evaluation, with a number like an F1 score, that often allows you to make much more efficient use of your time when you're trying to develop an anomaly detection system. And we're trying to make these sorts of decisions like how to choose epsilon, what features to include, and so on. In this video, we started to use a bit of label data in order to evaluate the anomaly detection algorithm. And this takes us a little bit closer to a supervised learning setting. In the next video, we're going to say a bit more about that. And in particular, we'll talk about when should you be using an anomaly detection algorithm, and when should we be thinking about using supervised learning instead, and what are the differences between these two formalisms.